So this part of the dynamics will be looking into cylindrical components for curvilinear motion. So application 1, then you have these second applications. So cylindrical component will be looking into particles that is moving cylindrically in a curve. Okay, so there are two components defined. One is the radial direction, that is the R, as you can see from the diagram, and the second, that is the transverse direction, that is the theta, as you look into the diagram, and then it is going in the counterclockwise direction from the horizontal. Okay, so that is what is written. Okay, the polar coordinates of the P is given as the vector R is equals to R times the unit vector in the radial direction. Okay, R extends outwards, and R extends outwards from the fixed origin, that is the point O or 0, and the transverse coordinate, which is theta, that is measured in counterclockwise direction, as I've said, from the horizontal. So if it goes in the clockwise direction, then you have to consider that as the negative direction. So the polar coordinates for velocity. So we know that velocity is actually equals to the derivative of any positions, radial or linear, with respect to time. So, and we know that the radial positions, as given earlier, the vector of R is given as R times the unit vector in the radial direction. So when you differentiate that with respect to time, okay, you have to use product rule for this. So you will get the R dot, that is the velocity in the radial direction, UR, which is the unit vector in the radial direction, R is the position, radial position, du subscript R is the unit vector in the radial direction with respect to time. So you have to apply chain rule here so that you can get the vector V is equals to the radial velocity with the unit vector of the radial direction plus the radial positions with the transverse velocity with the unit vector in the transverse direction. So the formula above, okay, the formula please remember. And then if you want to find the magnitude of the V, so you have to take you have to take the square root of the R dot square plus the R theta dot square. That is the formula to find the magnitude of the velocity of the particles P if it is moving in a cylindrical form. And for accelerations, we know that acceleration is the dv over dt, that is differentiating the v with respect to time. And then here, okay, you have to substitute the v that we have found earlier, that is R dot U subscript R plus R theta dot U subscript theta. So UR, remember, is the unit vector in the radial direction, and U subscript theta is the unit vector of the transverse direction. Okay, so after manipulating, after the manipulations, the acceleration can be expressed as what is shown there. So what we need to know is the R with two dots on top. That means you have differentiated the R with respect to time twice. The theta dot will be differentiating theta with respect to time once, then you square. So R is the radial position. UR is the unit vector in the radial direction. Okay, so R theta with two dots on top, theta with two dots on top, actually we are referring to the differentiation of theta with respect to time twice. That means you have to differentiate theta with respect to time twice in order to get a theta with two dots on top. and then the r dot, okay, is differentiating the r with respect to time once, and the theta is differentiating the theta with respect to time once. So that is d theta over dt, r dot is dr over dt, theta double dot is d squared theta over dt. So for the acceleration, remember the term with r double dot minus r theta dot square is the radial acceleration. The r theta double dot plus the 2r dot theta dot is the transverse acceleration. So when you take the square of both and then square root, you will be able to find the magnitude of the acceleration. Okay, for cylindrical coordinates, an extra direction or an extra axis here, that is the z-axis. So you have to consider that it is moving vertically upwards at the same time. So, and it is given as r subscript p. P represents the positions of the positions. P actually referring to the particle. So r is the radial position of the particle p. Is equals to the sum of r ur and z u z z. So ur is the unit vector in the radial direction, and u z or z is the unit vector in the z direction or the vertical direction. So, and then taking the time derivative and using chain rule, so you will get to this formula, that is r dot ur plus r theta dot u theta plus z dot uz. That is the velocity of the particle, and the acceleration of the particle also as shown there. So as compared to the previous one, for the velocity you will have to add in the z component, and for the acceleration also the same, where you have to add in the z component. Now here is the first example. So given that the question has given us theta is equals to 4t to the power of 3 over 2. So that means this is a function of time. So it is advisable for this theta, you differentiate it with respect to time once to get theta dot, and twice to get theta double dot. So because later we will be using the theta dot and the theta double dot. And for the radial position, that is r equals to 0.1 t cubed, which is also a function of time here. So you can differentiate r with respect to time in order to get the r dot, and differentiate it with respect to time twice, you will get the r double dot. Advice is to find out all the transverse components and as well as the radial components for position, velocity, and acceleration first before solving the problems. So here is the solution. So you have r, which is equal to 0.1 t cubed. Differentiating it once, you got 0.1 t square. Differentiating it twice, you got 0.6 t. And then for theta, you have 4t to the power of 3 over 2. Differentiating it with respect to time once, you have theta dot, so you have 6t to the power of half. Differentiate it for the second time, you have 3t to the power of negative half. So, and since the question has given us the time, which is equal to 1.5 seconds, so what we need to do is substitute t, which is equal to 1.5, to all the above. So for the r dot, r double dot, theta dot, and theta double dot. So you get the values of the respective components. So in order to find the velocity, so what you have to do is you have to take the square root of the 0.675 plus the square of 2.48. Okay, you have to take square root of 0.675 square plus 2.48 square. So you can get 2.57 meter per second, which is the magnitude of the velocity. And for the acceleration, you can do the same thing also as well, so that you get the magnitude of acceleration for this is 20.4 meter per second square. So second example here, so this is just almost the same thing. What you need to do is you have to have the R with one dot, the R with two dots, the Z with one dot on top, and the Z with two dots on top. Then you have theta with one dot on top, and the theta with two dots on top. So after that, you can substitute all the time which is equal to 3 seconds into the components that you have got. By substituting the time equals to 3 seconds, you will be able to find the magnitude of each of the components. So here is the working. So you can refer to this working for the theta and the z. So substituting in the formula to find out the magnitude of velocity of 24.5 meter per second, and then for the acceleration also. So you have the acceleration, magnitude of acceleration is 11.4 meter per second square. Remember substituting the 1.5, and remember to find the time derivative of r, first order, second order, the theta derivative, okay, time derivative, first order, second order, and the z, first order and second order as well. So then you take the square of each of the components, then square root, you will be able to find this 11.4 meter per second square. So that's all for today. See you tomorrow.